So this is my lab for energy for a spring system. So the goal of this lab is to analyze the motion of a pulled spring. We must analyze the forces acting on each point as well as their energies. And the end goal is to predict the motion of the spring and confirm if energy is conserved. I recorded a video and recorded the position at 96 equally spaced time intervals. Then I created a visual model in GlowScript as well, which predicts the motion and compares with actual motion. And it uses the kinetic energy, potential energy of spring, gravitational potential energy, and energy principle to show whether or not energy is conserved. The results show that the model matches the actual motion pretty well, and energy seems to be conserved within the system. So I uploaded a pre-recorded video into Tracker and recorded the position of the mass in 96 equally spaced time intervals. And I used the data to determine the stiffness of the spring as well as the relaxed length of the spring. So how do I do that? I considered a situation of static equilibrium to the right. Then I used finding stiffness, I used k equals 4 pi squared m over the period squared. And now I find the period to be founded to be 1.615 seconds, and the mass is given to be 0.402 kilograms. So I solved k to be 6.878. Then I also took the used the momentum principle and found that F net is equal to F spring plus mg is equal to 0 because it's an equilibrium. And I expanded it to be the force of spring is equal to mg, and I solved for the relaxed length, which was found to be 0.127. Now the principle used in the code. I use the momentum principle to update the position as we know by now. I use the position update formula as well, again, which we know by now. A new thing that we didn't use in previous labs is the energy principle, where the work from the surroundings is equal to the change in energy. And we determined there is no work, so the change in energy is equal to 0 is equal to the change in gravitational potential energy plus the change in kinetic energy plus the change in spring energy potential. Now we see here the formulas. So here are the formulas for the different potential energies, and I expanded them here to the right to show what each means. And yeah, now the code. I first calculated F net, and I took into account all forces acting. So there's gravity in the negative y, there's the force of spring times L hat, and I added them together to find F net. And uh, it updates every single time step, and it uses the calculated constants from before. Now, updating position and velocity, as you know by now, we use the momentum principle and the position update formula. Now, calculating the change in energies. So it uses the definitions of energy before and calculates all the different energies separately and adds them together. As seen here, energy total is equal to all the energies added together. And all potential, kinetic, and total energy are calculated before and after the time step. So here, as you can see here, you find the change in kinetic energy by taking the kinetic energy currently minus the kinetic energy in the time step before. So that's how you find the change. Now, it also compares the tracker data with the predicted data. I converted the tracker position data into a CSV file, and it overlays, as you can see here, the tracker data with the model data. The model is the blue, and the tracker is the red. Conclusions. I found the position data from tracking the model show strong resemblance. I found it to often overpredict the actual data, could be due to numerous errors mentioned below. Now I found that total energy was conserved. Change in total energy was always 0, which makes sense due to no external work. Now, as you can see here, green is the spring potential, red is the gravitational potential, and blue is the kinetic energy. And when spring potential is largest is when gravitational is smallest. Makes sense because when potential spring energy is maximum, potential gravitational is a minimum. And this is when the spring is pulled the furthest down. Now, possible sources not calculating initial conditions due to L0 or K. Human error when plotting data on tracker, dissipation of energy because we didn't factor in air resistance into our model. Now, is the energy principle satisfied? Yes, because the change in total energy is always 0, and our data follows that. The period of oscillation, oscillation in the y's and the x are both about the same, which shows that the period of oscillation match each other in the x and the y. Thank you very much for listening, and yeah, thank you.